was debating a lot about what to talk about. This would be something which would be very topical for a conference on spaces of tensor categories. And here I have sort of the higher categories. And the results about higher categories, mechanism to produce spaces of various categories and structures on those spaces. And sort of where the ideas here for this talk is to understand what kinds of spaces you get, what kind of structures, and then to use some techniques from topology and homotopy theory to then use those spaces and structures to maybe then say something about tensor categories, maybe putting structures that are known about tensor categories into a broader context, maybe sometimes providing new results, new theorems, or new structures. So that's sort of SON actions. So I'm going to be talking about the anatomy of SON actions here. N is probably going to be pretty small. And I should say all of this is joint work with Chris Douglas and Noah Snyder. And we did a lot of this quite a while ago and wrote most of a paper that never got finished because we always wanted to add more things to it. And well, we've recently realized that's stupid. So we're just gonna use that paper without the new things we wanted to hopefully read more about this stuff soon. Okay. So the first sort of way that higher categories can give rise to spaces is through the homotopy hypothesis, which says that if you have an n groupoid, that's the same thing as a homotopy n type. So a topological space with only homotopy groups that are non-zero up to dimension n. And already this gives us a way to associate various spaces to create various spaces of tensor categories. So if you can construct a higher category of tensor categories, then inside that is a higher groupoid, and therefore you get a homotopy type, and you can study that. So we've seen that today. We've seen that several times. So there's like the Morita category of tensor categories, bimodule categories, functors, and natural transformations. So sitting inside that, we have the core. So this is where you throw out everything which is not invertible. Okay, so I might also denote that with a little squiggle like that. Okay, so in this case, this was a 3 category, so you get a 3 type. There's also higher Morita categories and braided monodal categories. Monodal categories, which are modules for the braided one, and you can do the same thing. And you get a 4 type. Okay. And so you could study the topology of these 4 types and 3 types, and that's well, 4 types and 3 types are not that rich spaces. They're not as complicated. Okay, so there's some stuff you can say. They have more structure. These are symmetric monoidal categories. So you have what might be called an E infinity structure here. That's kind of doesn't help you a lot in general, but there is some part which does help you if you look inside of it. So inside, you look at the tensor invertible part, the pick of the Morita category. And now you have stable 4 type. This is like part of a spectrum that's just a small little piece of the spectrum that has these homotopy groups from pi 0 up to pi 4. And so, for example, we saw that pi naught of this space was this quantum width group. If you're away from the invertible part, it's harder to say. interesting stuff using the symmetric Monod structure. So this is sort of the vanilla way in which you can get spaces of tensor categories or structures on spaces of tensor categories. But there's another way in which these spaces arise, which gives you additional structure on these spaces, which is interesting. And that's through TFTs and the cobordism hypothesis. So I want to give a little bit of a recollection as to what the cobordism hypothesis says and how it relates to these spaces and what it predicts about these spaces, and then go from there. So the cobordism hypothesis has really two parts. Okay. So part one, that's that extended framed TFTs, so symmetric monodal functors from the Bordism D category, where all your manifolds are framed, tangentially framed, into any target. So this is some symmetric monodal D category, that's your target. That's the same thing as we take inside C, there's the fully dualizable. So objects have duals, the morphisms that witness that duality have themselves adjoints left and right, and so on and so forth, as high as it makes sense to go. And then you take the space of that. So the TFTs form a space, and this assignment takes a particular TFT, evaluates it on the point, and that gives you an object inside this space. So you can then go and ask if you have some particular higher category. You can then ask, okay, what are the fully dualizable objects in that category? What are the fully dualizable objects? So here are some various examples. So if you look at the category of vector spaces, then the fully dualizable part are the finite dimensional vector spaces. Look at the usual classical Morita category of algebras, bimodules, and bimodule maps. And then the fully dualizable part, and this is maybe, I'm thinking I have a perfect field. A perfect field, then these are going to be the finite dimensional semi-simple algebras. Look at the Morita category of tensor categories and bimodule categories, finite tensor categories, bimodule categories, functors, natural transformations. And here maybe I want to say that we're also algebraically closed and characteristic zero. And you get the multi-fusion categories. And we saw something similar in D equals 4, and you look at this Morita 2 category, this Morita 2 category that we saw earlier today of multi-fusion, graded multi-fusion categories. And there. Okay. So each of these then, in light of this first part of the cobordism hypothesis, is supposed to give rise to a framed d-dimensional TQFT. I also want to mention here, this is sort of, there's so Chris, Noah, and I focused a lot on this case 3, and we showed that, yeah, the multi-fusion categories are these fully dualizable objects. But in the course of doing that, we learned some things about general tensor categories, right? So the way this works is you have to show that certain morphisms have adjoints, and those adjoints then have adjoints, and so forth. So you kind of have to do this process inductively. So we showed that, and I should say that this fluidizable, talking about that, this is really has a parameter, has a dimension parameter. So it's sort of implicit when I say fluidizable, but really there's a dimension for it. So like the one fluidizable vector spaces, these are 2 fluidizable, 3 fluidizable, 4 fluidizable. What we showed is that actually everything in finite tensor categories, this Morita category, is 2 dualizable. We have all the dualizability up to here. And then for the 3 dualizability, there's sort of 4 different pieces of data that you need to be fluidizable, corresponding to 0 handles, 1 handles, 2 handles, and 3 handles. Now you don't have that for a general tensor category. We have most of it. I have the stuff for 0, 1, and 2 handles. This is the very last step that you're missing. And so if you go and read like how the cobordism hypothesis is supposed to be proven, that leads you to a very interesting conjecture in this case, that that actually, let's see how to say it. So each object inside this Morita category of finite tensor categories actually gives you a kind of TFT. It's not quite a full 3-dimensional TFT, but 3 in this case, framed. I'll put the little NC here, non-compact. So you can define it on all 0, 1, 2 manifolds, and you can define it on those 3 manifolds, which you can build using 0, 1, and 2 handles. So all of the Bordisms have some non-trivial outgoing boundary. Okay. So you get something which is like not quite a full TFT, but is still kind of in that same game. And maybe more generally, you would say that the functors from board 3 frame non-compact are into this target 1 are 1, 2, or 1 finite, and then make it core. That's sort of part 1 of the Bordism hypothesis. Is okay, right? Dimension 2, right? These give you these 2D TFTs that I can evaluate on frame manifolds. There's not that many framed manifolds, so it's not that great. It's better maybe in dimension 3 where oriented 3 manifolds can be framed. So maybe get some TFT stuff like that. But we can do better. So part 2 of the cobordism hypothesis is about what happens if you don't want framed things. What about other things? And the first observation for part 2 is already very interesting. It says that, well, the Bordism category itself has an ON action by changing the framing. The frame Bordism category has an ON action. So if you build a model using your favorite model of infinity D categories, it literally has an action by OD. So OD acts on this word frame D. So it's sort of a transference principle. If it acts on object and you map that object into something else, it acts on the mapping space. So this tells you that OD acts on this category of fluidizable tensor categories. So the multi-fusion categories, or maybe, okay, or the, braided multi-fusion categories. Frame guy also acts on this guy. So same principle to tell you conjecturally that you get an action on this category of all tensor categories. So the problem is that this action here is transferred through something which is like a homotopy equivalence, right? So it's not a true action in the usual sense. It's a homotopic flip. call it an infinity action. So it's the best you can do if you pass it through a. Which makes sense because like the things that we're going to be acting on, like you have like this group, this orthogonal group, and you want to have it act on this guy. Well, what is this guy? This guy is something which is like actually categorical, algebraic. It's some like groupoid that I got from some category. So how in the world can a Lie group act on that, right? Something weird is happening. So what's weird is that, well, yeah, it's true. You have to just pass into some world of homotopical actions where everything is really homotopy theory. And then there's an action of some kind on that. So one of the things I want to get to is to try to pin down what that is exactly and try to, how can we work with those types of actions and say something actually concrete. Okay, so yes.
Uh, so do you know if do you have a similar conjecture or the braided category version that every object is 3D-lizable?
Right. So you'd want something like if you are delizable in the sense where you're like n delize, maybe like n minus one delize. Like suppose you're like 3 delizable plus the stuff for handles, then there exists the TFT like this.
Right. So do you think
There's two things. There's like, do you have a statement like that? And then also, what are the things which have the like 0, 1, 2, 3 handles down here?
specifically do you suspect that more two, except every object in there is 3D-lizable?
Um, yeah, I'd want to do it that way. I want to say everything's 3D-lizable, even without this separable, like it's just finite.
Yeah.
Okay. And then I'd want to say, well, if I maybe I'm even a little bit better than 3D-lizable, maybe I can define things on 0 handles, 1 handles, 2 handles, maybe 3 handles.
I'm sorry, that's what I mean. Do you think it goes up to degree 3?
I don't know. I wouldn't be surprised if it does. There's also a second.
No, it doesn't. It doesn't. I mean, I'm
What's that? It doesn't?
pretty sure it doesn't go up to.
Okay. So the answer is
An example where it doesn't.
Yeah.
okay. Okay, good. So I don't.
How about
I've done it.
for some of the lesser handles?
I think
Go
0,
that-
1, 2 euros.
You can still get something which is like, it just has less data, right? But it still be something kind of like, maybe though. Like this. I want to say too much, I mean, it's conjecture, right? So, but it's not just as straightforward as saying, oh, I have the data that I want to assign to those handles. There's more that you have to show.
Yeah, I get that.
Yeah. And in this case, it kind of, the more that you have to show follows from some of this Radford stuff. So I think it's true in this case, but I don't know about this case. Obviously, it's not quite totally analogous. Okay. So the second part of the cobordism hypothesis is implied in this. It says that if you have a group be mapping to ON, then the fixed points give you, then TFTs are given by fixed points. So we can look at functors from board the structure. So this means a lift from a lift to this tangential structure. So if it's a point, that's just a framing. And if it's SON, then we're talking about oriented theories. If it's spin, it's a spin theory. If it's ON, if this is like the identity map, then this is the unoriented boardism category. You get various flavors. And the theorem is that you take what you did in the framed case, take the groupoid of fully delizable objects, and you take the homotopy fixed points. So whatever this homotopy action is, it should be enough to define this homotopy fixed points. And then these are what give you the oriented theories. Okay. And so there's sort of two remarks about this. So the first remark is that even just the existence of the action is like additional structure and data on this category, on this space of categories. So it gives you some structure and it gives you maybe like results about that structure. So if that's old structure that we knew about before, it can give rise to theorems about that structure. And it can also give new structure and theorems about that. So I want to give some, demonstrate that kind of philosophy in some examples in a minute. But then the other part is that, well, if you have a fixed point, well, that gives you for a nice group action. So I take a complicated group action, it gives me an interesting type of theory, much more interesting than the framed Bordisms, like maybe oriented Bordisms. Then those TFTs give you invariance of your category. You can evaluate all of a sudden, you can take you can take these various manifolds of this type and use your TFT that you get from your category, your tensor category, and evaluate them. It gives you some interesting invariant of your tensor category. So we saw that earlier today, or earlier this week, sorry, not today, in David Reuter's talk, where he was looking at the super wit group. And down. And he's considering some element in there. And okay, so this gives you, it's invertible, it's fully realizable, it gives a framed, 40 TFT. Okay. But then he showed that it lifts to, was it just a spin 3 or was it a spin 4? I can't remember.
Spin.
Oh, total spin. Oh yeah, okay. So it gives the stable spin group. So it gives a lift to spin. And so that enabled him to sort of evaluate on the K3 manifold. And that gave an interesting invariant of this Witt group, So it allowed you to kind of like compute some interesting non-trivial invariance of this somewhat mysterious object, but something which is hard to do. That's sort of an example of something you could get if you construct and understand your fixed points. So I want to understand what these so-called quote-unquote actions are, these homotopy actions, and I want to be able to and what fixed points look like, and I want to illustrate some examples of how you can compute these things and what they do and how you can work with them. Okay. Homotopy actions and fixed points. So this group and it's acting on some space X. And here we're thinking of this as an N type. For some finite N, it's sort of a groupoid. Some kind of groupoid of tensor categories, what we should think of. So a different way to understand a group action on an object would be as a homomorphism, but here it's homomorphism to the automorphisms X. So this is going to have to be some kind of, A infinity homomorphism. So you have a map, maybe it's not associative. We have some data witnessing the associativity and higher coherence data all the way up. It's sort of a large gadget to deal with. And there's an easier equivalent approach, which is to look at the classifying space. So if I look at BG, I can look at B on X, and I can look at a map, an actual honest goodness map from BG to B on X. And these A infinity groups are equivalent, known to be equivalent to infinite loop space, or sorry, to just plain one-fold loop spaces. And we can go from here to a map of loop spaces, at least by taking the loop space at BG produces something equivalent to G, something equivalent to X. It'll be a loop map. So rather than working with these infinity maps and actual groups, we can pass their classifying spaces. So this is going to be what a homotophical action is for us. So given this looks like autoequivalences of the groupoid of tensor categories, natural automorphisms of those functors, transformations of those functors, everything invertible. If X is an n-type, then this is also an n-type, like a monoidal n-type. And so this thing will be an n+1 type. So we want to, so actions are maps from Glassman space BG into this. What about fixed points? So fixed points, so associated to this, there's a space, sometimes called this. Okay. So it's a vibration over B odd X, and it has fiber X. So what I want to say is that it's E X, and then I form the associated bundle by acting on X. Okay. And that literally makes sense to the extent that odd of X is an actual group and can actually act, but it's kind of not, if it's coming from a category and it's like a weak group thing, so you have to futz with it. But in the end, anyway, you get a vibration whose fiber is X, and that's a stand-in for this construction, because then we can say what fixed points are. So a fixed point, this is our action right here, map. So a fixed point for the action is then a lift. So we want to understand a map. And then given the map, we want to understand a lift. And I lift it. How can we understand that? Well, topology says that like the very first thing you should try is to use, you're mapping out of something, try to give it a CW structure. So topology says use CW structure on each. So the idea, so for example, for the action, so the skeleton, this down. So I have all these inclusions. And eventually, in the end, I get to the space I'm interested in, BG. X. So the idea is to describe the action by describing a sequence of these extensions through the skeleton. So if I've described the action already on the 2 skeleton, to get to the 3 skeleton, I have to attach some 3 cells. So what does that look like? It looks like I have some attaching map alpha going in here, and then I want to trivialize it. So 2, 3. So I want to have my attaching map of my 3 cell, and in order to extend to this is a push out, I need to trivialize that. So this data, this extension here, will be a trivialization of A2 composed with this attaching map alpha. Okay, maybe if there's lots of cells, you have to do this. Okay. if this is an n type or an n+1 type, eventually the homotopy groups vanish. And what that tells you is once you get far enough, so once you get to, skeleton n+1 of BG, well, then you have this n+1 attaching sphere for the next stage. Okay. Whether it's 0 or not, that's not something, it's not a choice. There's no choice there. It's either 0 or it's not. It's some kind of condition. So you get a condition. And then the other extensions will all be for free. They'll all be unique extensions to the rest. So in the end, you get like this finite amount of data if there's a finite number of cells like that. And for fixed points, the story is very, very similar. Right. For only now we have a kind of lifting problem. So maybe I'll write it sort of horizontally, point contained in the one skeleton of BG. It's contained in we have our action on X. We have this X here. And we want to lift this to a map from BG to here. And so we can try to do that one cell at a time going through our CW structure. So the first thing we would choose would be a lift like that. So that's a map from the point, which lives over the base point here. So it's an element in the fiber. So that's exactly an element in our groupoid. So it's an object. That's the first thing you'd want for a fixed point. There should be an object plus some data. And so the question is, what is the other data that we have associated to this? And this is this is sort of the relative question of like this thing. And so there's the whole machinery of obstruction theory, which tells you exactly the form of what the data is. And in each case, for an A cell, so to lift A cell, what you have to do is you can trivialize a certain map, which goes from SK-1 into the fiber. So this is some, K-1 automorphism of our chosen object. So you have to trivialize that particular K-1 morphism. And exactly which K-1 morphism that you have to trivialize, it depends on the action and on previous lifts, previous trivializations that you've done before. So out of those previous things, you can build a new thing, and then you have to trivialize that. And there's one for each cell. So the answer is kind of the same for understanding both the actions and the fixed points. And it says, find a CW structure and try to understand it enough so that you can understand these trivializations of these composite maps. So let's proceed and do that in some examples. Warm up, D equals 1. We have, 1D oriented is the same thing as framed. Sort of a happy accident. So these then are supposed to be the same thing as finite dimensional vector spaces. And you can even see that an example of that if I have a boardism that's an oriented boardism, it induces sort of kind of orientation for my objects, plus and minus. And so to a cobordism like that, I should, for a given vector space, I should associate something which pairing between the vector space and its dual going to our ground field like that. So you can see roughly how that might work. But there's supposed to be an O1 action on this groupoid of fully finite dimensional vector spaces. So how can we understand that? Well, we're supposed to understand it through its classifying space. Okay. Classifying space. This is BZ2. I know this. This is RP infinity. So it has this nice CW structure where it has a cell in every single dimension. Now I can start writing down that CW structure. So I attach a one cell, I get the sphere, and then I want to attach a cell to that. And I do it by the double covering map. Okay. So then I get RP2, and then I have an interesting map from S2 to RP2, my double cover map. Okay. And I attach, I trivialize that, and that gives me RP3. And then I try to go on. And I want to act on the groupoid of vector spaces. So vector spaces is a one category, so it's a one type, so B-OT is a two type. Okay. So once I get to, that means that there's data here and here.
Sorry, what's the tilde?
A groupoid. I'm acting the groupoid of vector spaces, and I have endofunctors of the groupoid of vector spaces. So in particular, I'm going to write down a functor, an endofunctor, but it's not going to make sense for any map of vector spaces, only isomorphic. Yeah. And then here, this is just a condition, and then forever after it's free. So this is it. There's these two cell attachments. So there's exactly two pieces of data which constitute a homotopical one action. And okay, so this first piece of data, that's something in I1 of B-OT X. Well, that's something in I0 of OT X. So I write like, this is like 1, this is like 2, and this is like 3. Okay, this is some endofunctor of the category. So here, this is like the data. So I have some functor from this groupoid to itself. Part 2, I'm supposed to precompose that by the doubling map. So that takes my functor and applies it twice. And then I'm supposed to trivialize that. So that's some natural isomorphism between squared and the identity functor X. And the third one is a condition on this functor. I'm just going to write it down because I'm quickly running out of time. So it looks like the following. Okay, so I can take the inverse of this eta to go from the identity to 2 Fs. Okay, I can withdraw another F, and then I can use eta over here to go back to the identity. And this should be the identity on F. That is exactly what an G2 action is. The Gordism hypothesis predicts that you have such an action. What is it? Well, obviously it's supposed to take an object to its dual. So the endofunctor, in this case, is takes an object to a dual. That's not a functor on all vector spaces, but it is a functor on the groupoid because it's supposed to be a covariant functor. So it is a covariant functor on the groupoid because we can invert morphisms. So you could use it as an inverse. Okay. Okay, so if I apply the vector, this functor twice, well, we know that doing the double dual for vector spaces is naturally isomorphic to the identity for finite dimensional vector spaces. Yeah. And it's, this is a natural isomorphism. Okay. And it does in fact satisfy this. Okay, it does. So then you could ask for fixed points. I'll just do that. So for fixed points, you need to trivialize this data. So for fixed points, well, for fixed points, what happens is there's a shift, right? This was an n+1 type. The fiber is an n type. So what happens is for fixed points, this one's still a new datum, but this one becomes a condition and this one becomes nothing. So the first one is you have to trivialize the functor, but just at the particular, so you pick an object that's sort of 0. Then we pick a trivialization of our functor applied to the object. So we need a trivialization, an isomorphism between V and V dual. So I can think of that as a non-degenerate pairing. And then it has to satisfy a condition. And the condition looks like if I go, let's see. So if I go from V to the double dual using my natural transformation like that, okay, maybe the inverse, then I can apply dual functor to this B, okay, that, and then I can apply B one more time, and this has to be equal to the identity of V. If you pick a basis and write down exactly what that means in terms of B, it tells you that if I take the transpose of B, compose it with the matrix for B inverse, that has to be the identity, which, given the fact that it's non-degenerate, is equivalent to it being symmetric. So we learned that we have a non-degenerate symmetric form. So which is something we knew, that unoriented 1D TFTs are vector spaces with a symmetric non-degenerate form. But this is how you can see that from this perspective. Okay. So what about SO2 actions? I want to talk a little bit about SO2 and SO3. But briefly, for the sake of time. So BSO2 is still something pretty nice. Right. Here's the CP infinity. It also has a nice uniform PW structure that we can understand. So if I wanted to do the same idea, so I want to first understand an action. So the first cell, this is CP1, is S2. Okay. So this is nothing. So then I have to do some data like that. Then there's a cell that's attached by the Hopf map. I'm going to call that Q for reasons that I'll keep to myself for now. But some map from S3 to S2 that's interesting. That's the thing I have to kill to get CP2. Okay. So this is some data. This is something in phi2 of these x. So phi1 of v aught, sorry, of aught x. So it's a loop based at the identity. It's a natural transformation of the identity. This is usually called S for the Serre. So S is something which goes from the identity of X to the identity of X. It's a natural transformation. And then this next thing, well, it depends on what you're acting on. If you're acting on a 2 type or a 3 type, whether this is data or whether it's a condition. So this part of the category of this thing. It looks like you have, there's this point here, it's a pointed object. Then we have the identity endofunctor, and then we have stuff above it. So the Sayre lives right here. Like two monoidal structures, two layers that are trivial. It's like a braided monoidal thing, like a universal braided muscle. So part of the data of the Sayre is something which acts a little bit like a braiding. So you can, it's natural, right? So what you can do is you can write down the following data. So I can take the identity functor, I can look at the Sayre, and I can look at the Sayre inverse. Let me write it this way, Sayre inverse, okay, like that. There's a morphism like that, going from identity to the composite of the Sayre and the Sayre inverse. What does naturality mean? Naturality means that if I have this component for each object, if I have my component of my natural transformation, and then I have a morphism, that supposed to get something witnessing that diagram commutes. So in this case, I can apply it to S inverse. That gives me a cell which fills this in. And then I can cancel them. This gives me a universal way to take something in pi 2 of this type of category and construct something in pi 3. So I claim this is the effect of applying Q to that. So here, you either get the condition that this is trivial, or if you're in high enough category number, you get the data that this thing should be trivialized. And that is roughly the story for SO2. So I'm going to jump ahead to SO3. And right. And it's a story because yeah, for the things that we want to act on, this is kind of all you need to do. Get up to that point. And you could look at fixed points for that too, but let me instead look at SO3. To kind of explain what that looks like. So BSO3, I'm going to be in the case where I'm going to be acting on a 3 type. So I want to understand it's 4 type. So I need to go up to 5 cells. And so this is maybe a theorem that the 4 type of BSO3 comes from a CW structure, which looks like S2 union a 3 cell, union a 4 cell, union 5 cell, and then there's higher stuff. So these 5 cells determine the 4 type of BSO3, and they can be organized as follows. So we start with S2, and we can add on to S2. So a priori, when you're building a CW complex, like the attaching maps have to land on all the previous stuff. So there's a happy accident. The 4 cell that I'm attaching here doesn't care about the 3 cell. It lands entirely on the 2 cell. In fact, it's exactly this 4 cell that we saw. So the inclusion of the 2 cell and the 4 cell, that's the inclusion of BSO2 into our type. So here I'm looking at just the 4 type. So this is really like CP2 for our purposes. And this is attaching the 4 cell. Okay. The 3 cell, what's the big difference between BSO2 and BSO3? Well, pi 1 of SO2 is Z, pi 1 of SO3 is Z mod 2. So in BSO3, I have to have something that fills the Z, makes it Z mod 2. So I can look at the attaching map for that 3 cell, given by attaching 2 to it, and I get the suspension of RP2. It's like what we had earlier, but it's suspended.
Your CP infinity or CP2? So below.
It's CP infinity, but if I'm acting on a 3 type, it might as well be CP infinity. Sorry. You should think of this as being the SO2 action. Okay. It's really CP2. Right. This is suspension RP2. This is attaching the 3 cell. And the 5 cell also miraculously doesn't care about the 4 cell. This lands on the previous stuff. And this is what I would get, at least as far as, it's not the whole thing, but it is as far as the skeleton is concerned. If you kill the first Pontryagin class, this is a structure that classifies two framings or P1 structures.
You meant to write BSO3 there, or?
Yes, yes, it's. Thank you. And then that's it. The rest is just sort of push outs. This would be, as far as the 4 type is concerned, this is essentially BSO3. So if you want to describe SO3 action, you have these 4 different pieces of data. You have your Sayre automorphism, which we described before. We have this trivialization of this weird thing. Called it W. Trivialization of that weird thing. And you have a trivialization of the square of the Sayre. So this, yeah. And you have a condition. So the Sayre, in this case, let me just say what this and what fixed points are. So the Sayre, this is the Sayre bimodule turns out to be equivalent to twisting by the double dual. This Radford isomorphism, this is all stuff predicted by the cobordism hypothesis. Just by dualizability, you're supposed to have all of this structure. This thing is a trivialization of the square of the Sayre, so it's a trivialization of the quadruple dual bimodule. So for tensor categories, it amounts to the fact that the quadruple dual functor is isomorphic to conjugation by the distinguished invertible object. This thing is a little bit more mysterious. But actually, we learned from David Alla's talk that the O3 action actually lifts to a smaller category number.
The O2 action.
The O2, sorry, not all of it, but the SO2 action lifts. So actually this stuff is in some sense trivial because of that lifting that David told us about. So I'm not going to talk about that. And then there's a condition that has to be satisfied. And so then you could then try to trivialize this data, right? And to give yourself a fixed point. So that would have some data corresponding to trivializing the Sayre, so trivializing this bimodule. You have some conditions, some data that would sort of evolve, being compatible with this Radford trivialization. And then you have an additional condition coming from this relation. And that would be it. And I could write that down, but I think I'm over time already, so I'll stop.
You're fired. You're supposed to ask for questions then.
You're right. Questions.